Rao Bhim 8.4. We are going to talk about minimal polynomial. But first of all, let me tell you that minimal polynomials are of very little importance for learning linear algebra. To motivate minimal polynomials, we consider this 3 by 3 matrix. We have already seen that if I take its characteristic polynomial, which is lambda minus 1 whole square times lambda minus 2, because we have got these two diagonal entries equal to 1 and one diagonal entry equal to 2. So if I evaluate this polynomial at this matrix, then I shall get the 0 matrix. So this is an annihilating polynomial for A. Now this is not the only polynomial which will do this job. For instance, I might very well multiply this with other factors that will also do the job quite well. So if I take some polynomial p lambda, which is this, times lambda minus 3, then goes without saying that even if I compute p of A, that will also be 0, because the fact that you already have this part will ensure that the result is 0. Now what comes as a bit more unexpected thing is that you can actually have a polynomial whose degree is less than that of the characteristic polynomial, which will also annihilate it. For example, in this example, I had this as my characteristic polynomial. I will just forget about this one. And if you evaluate PA, you will find even then you have 0, because this lambda minus A will, so when you compute A minus I, both these things will become 0 and this will kill this. So this is a polynomial which is not a multiple of the characteristic polynomial, and yet this is an annihilating polynomial. So the natural question becomes, what are all the possible annihilating polynomials? And that gives rise to the concept of the minimal polynomial. Definition 8.4.4, a monic polynomial of least degree that annihilates A is called a minimal polynomial of A. So let's clearly understand what we are doing. If I have a polynomial that annihilates A, that is PA is equal to 0, the 0 matrix, then if you multiply this with more stuff, then of course it will remain 0. So once you get something which is an annihilator, you can grow it. This naturally forces us to look in the other direction. How small can I make it? Because if some small thing works, then bigger things will also work. That is why we are looking for least degree polynomials. Try to make the degree as small as possible. Now if I have a polynomial that kills A, 2 times that will also kill A. So this multiplied constants are not going to play any role. Hence I want the polynomial to be monic, which means the highest degree term will have coefficient 1. For example, this is a polynomial which is monic because the highest degree term has coefficient 1. If I have here minus, then it will not be monic. Now the way the definition is given in the book, they are not using R and R here. They will say the monic polynomial and the minimal polynomial. Indeed, it is unique. That is not very difficult to see, because suppose F and G are both least degree polynomials and monic that annihilate A, so both of them must have equal degree, and FA is equal to 0 and GA is also equal to 0, that is the 0 matrix. I claim that then F has to be equal to G, because otherwise you just subtract one from the other, that will also be the 0 matrix. Now because both of them are monic, so whatever is the highest power of F, suppose that was some x to the power k, that came with coefficient 1 in F, that also came with coefficient 1 in G. So when you subtract one from the other, this highest term is cancelled off. So this thing must be a polynomial of degree less than or equal to k minus 1, and that contradicts the fact that F and G were both supposed to be least degree polynomials annihilating A. So F minus G is an even smaller degree polynomial which also annihilates A. That shows that we can actually write the monic polynomial of least degree is called the minimal polynomial of A. Now, as we have already seen, once we get something which annihilates A, every multiple of that polynomial will also annihilate A. Now we are going to make a very strong statement which will say that all the annihilating polynomials must be multiples of the minimal polynomial. So it gives a nice structure to the set of all annihilating polynomials. Theorem 8.4.5. We have a square matrix. It has minimal polynomial, say f lambda, and I take any other polynomial. Then I say that this p will be an annihilating polynomial if and only if the polynomial f divides the polynomial p. This is the sign of divides. That is, if you divide p by f, the remainder will be 0. Now, the theorem as stated in the book is not exactly this. The theorem in the book says that this part only. Now, the other part is actually quite trivial, and it is this two-way thing which makes this theorem powerful, because if f divides p, then p must be something times f, and f itself kills a, so if you multiply that 0 with something else, it remains 0. So this implication is just trivial. The non-trivial part is this implication. So for this part, we are starting with the fact that pa is equal to 0. I have to show that f will divide p. That is, if I do long division of the polynomial p by f, the remainder will be 0. I do not know whether the remainder will be 0, but I can do the following thing. I can write p lambda equal to some q lambda times f lambda plus r lambda. So what I have done is I have just done long division of p by f. This is the quotient part and this is the remainder part. In case you are not quite comfortable with this, think of our high school days where we learned to divide polynomials like this. So when we are dividing by this, we are getting this as the quotient and this as the remainder. So this is what I am calling q, this is what I am calling r, this is the dividend, in my case p, and this is the divisor, in my case f. So when I want to show that f divides p, I have to show that the remainder r lambda is 0. Now we know from the property of polynomial division that the remainder must have degree less than this, because otherwise I will have continued one more step. So I have some such thing. That is true for any f and any p. Nothing very profound. Now I know that pa is equal to 0. I know that fa is equal to 0. So first of all, in place of lambda, I can safely put a, and that will continue to be valid because matrix multiplication has the same properties as ordinary multiplication, except that matrix multiplication is not commutative, but here we are multiplying only powers of a, so that is commutative. So you can just plug in matrices and still the equality will hold. Now I know that fa is 0, so this is not there. Pa is 0, which naturally forces Ra to be 0, which means that R is an annihilating polynomial for A. But that cannot be, because degree of R is less than the degree of the minimal polynomial. The minimal polynomial was supposed to be that polynomial whose degree is the least possible among all annihilating polynomials. So here I have given you yet another annihilating polynomial which has even smaller degree. That gives you the contradiction, proving this side of the theorem. So in particular, minimal polynomial must divide the characteristic polynomial, because characteristic polynomial is one annihilating polynomial. Naturally, a lot of speculations now may be made as to what is the minimal polynomial. So if I know the characteristic polynomial, I have to drop various factors to get to the minimal polynomial. So let's take an example. So this is the matrix that I started this lecture with. In this case, the characteristic polynomial may be computed quite easily. Lambda minus 1 whole square, lambda minus 2. So is this the minimal polynomial? We have already seen that the answer is no. I can actually drop one of these lambda minus 1 factors and still get an annihilating polynomial. So I have at least reduced the degree by 1. Can I reduce it further? If I have to reduce it further, I have to either drop this or I have to drop this, and it is quite easy to say that dropping any one of them will not keep it an annihilating polynomial. For example, if I drop this, I will be left with lambda minus 1. If I evaluate it at a, I will get a minus, the role of 1 is played by I, and that will have 0, 0, but this 2 will only go down to 1, so it will not be the 0 matrix. Similarly, lambda minus 2i will kill this, but will have minus 1 here. So in this case, I can say that this is the minimal polynomial. Now from this, there are a number of things that might come into your mind. One is, if I have any such powered things, you forget about the powers, retain only one term of each. And the other thing is, maybe for some matrices, you can completely drop one of these things. Now, the first theorem that we are going to do now says that you cannot completely drop any of these terms. Theorem 8.4.6, I have taken the liberty to cast it in a form which I think is more intuitive. I have a square matrix, f is the minimal polynomial, chi a is the characteristic polynomial. Then I know that f will divide chi a, which means I want to get, in order to go to f from chi, I have to possibly drop some factors. Now it says you cannot drop some 0 completely. It must have all the zeros of chi a. Thus, if your chi a is like lambda minus 1 to the power 5, lambda minus 2 to the power 3, and lambda minus 3, in that case, you cannot drop lambda minus 1 altogether. You can reduce this number. You can reduce this number from 5 to 4 to 3 to 2 to 1, but you have to have at least one lambda minus 1 factor in the minimal polynomial as well. Similarly, you have to have at least one lambda minus 2 and at least one lambda minus 3. So this is a possible candidate, this is a possible candidate, but this is not a possible candidate because you have completely dropped 1, 0. That is not allowed. Now, of course, the reverse implication is also true, because if you have something which is a 0 of f, then it must be a 0 of chi a, because f anyway divides chi a, that we have seen in the last theorem already. So I start in the proof by taking some 0 alpha of chi a. I have to show that f must also be 0 at that value. Now, if alpha is a 0 of chi a, which is the characteristic polynomial, it basically says that alpha is an eigenvalue of the matrix A. Now we know that if I take a matrix and its eigenvalue, if I take square of the matrix, then square of this will be an eigenvalue, cube will be an eigenvalue, and in general, if I take any polynomial of A, the corresponding polynomial of alpha will be an eigenvalue. I am going to invoke that result using my minimal polynomial f. So f alpha is an eigenvalue of fa. But what is fa? Fa is minimal polynomial, in particular it is an annihilating polynomial. So this is nothing but the 0 matrix. So f alpha is an eigenvalue of the 0 matrix. 0 matrix has only one eigenvalue. So I must have f alpha equal to 0, completing the proof. Now let's take an example. Suppose I have some matrix whose characteristic polynomial is this. So 1, 2, 3 and 4 are its eigenvalues with algebraic multiplicities 3, 5, 1 and 6. I am interested in finding out the minimal polynomial of this matrix. I know that it will be a factor of this, so I have to retain some amount of lambda minus 1, some lambda minus 2, lambda minus 3 and lambda minus 4. I know that I cannot drop any of these roots completely, so I will naturally try to reduce these powers. In particular, I cannot reduce this power any further because it is already 1. So lambda minus 3 must be there. So the first guess that might come to our mind is that, well, you keep only one specimen of each 0. Is that going to be the minimal polynomial? Well, the answer turns out to be no, always. Sometimes it is, but sometimes no. Now, there is an interesting class of matrices for which this idea will work. Just forget about all the powers, keep exactly one copy of each and it will work. For one type of matrix, it is going to work, and that is a very important class of matrices. And this is the statement of theorem 8.4.7. Suppose A is a diagonal matrix. So that is the class that I was talking about. Then I can write down the minimal polynomial just by looking at it. It will be lambda minus d1, lambda minus d2 up to lambda minus dk, where these di's are the distinct diagonal entries of A. Notice that I have written n here and k here. K is in general less than or equal to n. Let's look at an example. Suppose A is this diagonal matrix. I can see that the diagonal entries are 1, 2 and 3. 1 has been repeated twice, 2 has been repeated thrice, and 3 has occurred only once. So I can immediately write down the minimal polynomial as lambda minus 1, only one copy, lambda minus 2 times lambda minus 3. So, in this case, that idea works. Namely, you keep only one copy of each. But that may not work for an arbitrary matrix that is not diagonal. The proof here is super trivial, because if I just evaluate A, put A here, it is A minus I, then A minus 2I, like that, and A minus 3I. So A minus I will have these things equal to 0. Then A minus 2I, when I multiply with that, the things that are already 0 will remain 0. This will further contribute, these things are 0. And finally A minus 3 will contribute, this is 0, and everything will become 0. And you cannot drop anything more. So the proof is quite trivial. Just in case you think that this idea is going to work even for non-diagonal cases, here is one non-diagonal matrix for which it is not going to work. So in this case, I can easily say that my characteristic polynomial is lambda minus 1 whole square, because it is a triangular matrix. So if I blindly apply that idea, I will say I will keep only one copy of lambda minus 1. So the minimal polynomial is lambda minus 1. That's not true, because you just evaluate this at A. It will be A minus I. This is my A. So A minus I will be just how much? It will be 0, 0, 0. But this one will become minus 1. No, this one will become 1. So it is not a 0 matrix. So you see, the idea of keep only one copy of each such factor does not work in general. It works for diagonal matrices and it works for some other matrices also. But here is at least one counterexample for which it does not work. Let's take a look at our fundamental diagram that we have seen earlier in another video also. So I have this idea that whenever I am given a linear transformation from Rn to Rn, I can represent it as a matrix. Now this matrix depends not just on the linear transformation but also on a chosen basis. So you have to choose a basis of Rn. With respect to this basis, the linear transformation will have some matrix representation. So to say that the matrix is same as the linear transformation is not entirely correct, because you have to take into account the choice of the basis, which is typically arbitrary. So the properties of the matrix that we see are partly owing to the property of the linear transformation and partly owing to the property of the arbitrary basis. Naturally, we are interested in only those properties of the matrix which come from the linear transformation and not from the basis. So even if you change the basis, the matrix will change, but those properties will not change. So those are the properties that we work with in linear algebra, not just any property. I have already mentioned that if I am given a square matrix, then the trace, namely the sum of these diagonal entries, is one such property. Change the basis, the matrix changes, but still this diagonal sum will not change. The diagonal entries will change, but the sums will not change. However, if I add these entries, in that case, change the basis, the matrix changes, and so may the sum. That is why we never care about the sum of these diagonal entries. So whenever we are talking about any function of a matrix in linear algebra, typically it is seen that it is invariant under the choice of the basis. Now our minimal polynomial is no exception. It says that suppose you fix the linear transformation, take any basis, you get a matrix. Call this matrix A1, and for a basis which I call B1. Well, you find out its minimum polynomial, call it F1. Now you keep the same linear transformation, choose a different basis B2. With respect to that, you get a different matrix, compute its minimal polynomial, call it F2. Then there is a guarantee which says that F1 must be equal to F2. In other words, the minimal polynomial is a property of the underlying linear transformation and not a property of the arbitrarily chosen basis. Theorem 8.4.8, which just writes in a rigorous way whatever we learned here. If A1 and A2 are similar, then they have the same minimal polynomial. Now, I hope you remember what is meant by similar. By similar, I mean that there is a non-singular matrix such that A2 is P, A1, P inverse. Now, what does this have to do with this? Because every time you change your basis, this matrix changes in a particular way, and that particular way is it gets pre-multiplied by some non-singular matrix. This non-singular matrix depends on what basis you were working with and what basis you are changing to. Sometimes this P is called the change of basis matrix, and we will post-multiply it by the inverse of the same P. So A2 must be of this form. So every time you change your basis, you get a suitable non-singular P, and the new matrix will be related to the old matrix by this relation, and it is such a commonly used relation that we have a name for it. We call it similar matrices. So whenever A1 and A2 are similar, meaning whenever they represent the same linear transformation, possibly with respect to different bases, then they must have the same minimum polynomial. And the proof is absolutely trivial. So I want to show that the monic polynomial which annihilates and is of least degree is the same for A1 and A2. Well, I will show something way stronger. I will show that the polynomial annihilates A1 if and only it annihilates A2. So the set of all annihilating polynomials of A is equal to the set of all annihilating polynomials of A2. So if the entire set here is equal to the entire set here, then naturally you pick that unique monic polynomial whose degree is the least here, and you do the same here. You will get the same result because they are the same set after all. So if I can show this, I will be immediately done. Now how do I show that one set is equal to another set? Simple. I take anything here, show it is there. Take anything here, show it is there. Now A1 and A2 in this theorem are pretty similar. So they are similar actually. So the relation is symmetric. So if I can show that anything here is there, I can use the same argument to show that anything there must also be there. So enough to prove that if I take any annihilating polynomial of A1, suppose f of A1 is equal to 0, I will show that f of A2 must be equal to 0. And that is simply because, just observe this, that similarity transform plays very nicely with power. So if I have this, raise this to square, this will also be raised to the square. And why is that? Because P A1 P inverse, P A1 P inverse, this P inverse P cancels off, so you are left with P A1 square P inverse. And similarly, whatever power you put, you will always get this thing. In particular, whatever polynomial you put, you will get the corresponding polynomial here. So this is nothing but f of A2, I want to show that it is equal to 0. This is actually nothing but P f of A1 P inverse. Now f of A1 is 0, so this has to be equal to 0. So immediately I get this theorem. So that's essentially all that I wanted to talk about, or this chapter talks about minimal polynomial. We can come up with some more stuff once we develop some results about when a matrix is similar to a diagonal matrix, because for diagonal matrices we have a very nice way of writing down the minimal polynomial. This theorem says that if a matrix is similar to a diagonal matrix, then we can use the same idea there too. Now we shall take this up in the subsequent videos when we move to the next section.